Alright, last video in chapter 1. Let's talk about mixtures. A mixture is a type of substance that can be physically separated, meaning the parts that make up the mixture, right? It's a mixture, the things have been mixed together. If it can be separated through physical means, meaning we don't need a nuclear reaction, we don't need a chemical reaction, we can just pull them apart. Now, the way we pull them apart can be pretty tricky, don't get me wrong, but we have to be able to do it physically. We have homogeneous mixtures, right? So HOMO means same. So I remember that just by this prefix right here. It's the same all the way through. So a homogeneous mixture has visibly indistinguishable parts. I mean, you can't tell the difference because it's the same all the way through. It's mixed up really, really, really well. Hopefully you didn't miss my story about homo and heterogeneous mixtures involving brownie batter in Gen Chem. If not, you missed out. But we call these solutions, right? When these things are mixed together. And solutions, we typically, I mean, most of them that we use in lab are in the liquid state or aqueous phase, but they're not always wet, right? That's the obvious example is, you know, a liquid, aqueous solution, but air is a solution because it's a mixture of stuff, right? And it's just, it's very equally spread out, very evenly mixed. So it's indistinguishable. You can't visibly distinguish, you know, this type of air from that type of air. They can also be solid, so an alloy or cement are examples of solid solutions. Right? Boop, boop. So an alloy is a mixture indistinguishably mixed, a combination of different types of metal. Right, but obviously most metals are solids at room temperature. Cement is a mixture of pebbles, right, and they solidify, but that is a solution. We also have heterogeneous, right? Hetero means different, and so what this means is that there's a visibly distinguishable part in this heterogeneous mixture. You can tell the difference. When I was growing up, it was really hip. It was a cool thing to make these little bits of artwork. You get like this glass container, maybe a mason jar or something, and you would make these layers. You'd carefully put in these layers of colored sand, so like blue sand right there, and then I'd carefully make this layer of red sand right there, and then I'd have this layer of, I don't know, orange sand, and then white sand, and tan sand, and I don't know, purple sand. And I have all these different layers of sand. Now, these have been mixed together in the mason jar, but I can clearly see the difference. Like, that's actually the point here, is that I can see the distinguishable parts. Now, you know, as a turd of a young boy that I would always take these mason jars or these things, and I would just shake them up really, really bad so that they would mix evenly amongst themselves. Taking this once heterogeneous mixture and turning it into a homogeneous mixture. Now they're mixtures because if I had a lot of spare time and nothing else better to do, I could grain by grain separate physically with my hands, physically separate these different types of sand, and so that's a mixture that can be physically separated. Oops, wrong page. So there are a couple different kinds, right? So we have paper chromatography. You might have done this in biology. I'm not sure, to be honest. I think I did it in biology when I went to this school, but that was a long, long time ago. But this is paper chromatography of ink. You might have done it with chlorophyll. If it sounds familiar, there was this piece of paper. It's a type of filter paper, right? And you would mark this line right here with a pencil as a reference, and then you would mark ink on the paper initially, and then what you would do is you'd have this small crucible or a little bowl full of some solvent, right? Some solvent, and what would happen is this liquid that was in the bowl would move up the paper through like a wicking action. It would like wick up. And what would happen is, you can't really see it in this black and white, but you can see these shades of gray, is that the different pigments that would be in that ink would separate out based on their attraction to this filter paper, right? You see things like, yellow pigments, don't travel quite as far because they're more attracted to the paper. Purple and blue pigments travel a little bit further because they're not quite as attracted to the paper. And it's a pretty elaborate system, but you're separating this mixture of inks based on their attraction to paper. But you're doing it by physical means because you're not changing the nature of the ink at all, right? No chemical reactions, no nuclear reactions, just physical separation. Distillation is probably something that you've heard of before. This is also a means of physical separation. It is pretty darn elaborate. If you don't know what it means to distill something, this is a typical chemistry lab apparatus for distillation. What we do here is we get this, this liquid solution that we want to distill here, and it's typically some type of alcohol or some organic substance that has a lower boiling point than water. And so what we do is we have this substance in here, and in my experience, these labs, there's about a 20-ish degree difference in boiling point, right? So we have water turning into the gas phase at about 100 degrees Celsius. And then we have various types of alcohol. I think the last one I did, I think its boiling point was about 83 degrees Celsius. So what we would do is we would heat, using a Bunsen burner, we would heat this distilling flask to a temperature that was above 83 degrees Celsius but below 100 degrees Celsius, right? It's very important that you don't get up over 100 degrees Celsius, and hopefully you'll see why in a moment. So let's just say I perfectly maintain a temperature of 90 degrees Celsius. Let's just say I'm gravy at that. I set this burner at the perfect distance. I maintain it with a perfect amount of flame, and this system is at 90 degrees Celsius. The alcohols in this flask are going to evaporate because that's above their boiling point, but the water is not. And so what's going to happen here, and here's the thermometer through which you read, right? The alcohols will vaporize, they'll turn into gas, and they'll float up this tube, and they'll float up here, and then they'll kind of naturally flow this way because, gases expand to fill the shape of their container, so they'll fill this way. Now, as they move this way, you are actually pumping cold water. This is like a special tube that you can pump water through, but it doesn't get to this middle tube. That is the middle tube right here. And so gas can travel down in here because it's expanding to fill the shape of its container, but this cold water around it is actually getting it to cool down. And so what does this alcohol, this gaseous alcohol do? It condenses from the liquid state back into from the gaseous state back into the liquid state. You can see that we have these little drops right here falling into the receiving flask. You might wonder, what about the gas, that alcohol gas that comes up here and fills in here? Well, it'll eventually condense or condensate back out, and it'll fall back into the flask, and it'll evaporate again, right? And so most of it will move through this condensing tube eventually, right? And then in lab we would do all these tests on the distillate that we would get, and we would figure out how well we did. But these are different types of physical separation because that's the key. You have to be able to separate a mixture physically. Last thing, the opposite of a mixture is a pure substance, right? So a chemical like water, even though it has hydrogen and oxygen in it, it's always H2O. It's pure H2O. That's one molecule. That's one substance. Carbon dioxide, and anything that's a pure element like O2 or H2, nitrogen gas, something like that. If it's a pure substance, it's just that one thing. Compounds can still be separated into individual elements, just not through physical means. There's going to require a chemical reaction. Electrolysis is a common chemical method for separating compounds into elements. right? Remember, if we take H2O and we add an electrical current, we will actually generate O2 and H2 gas. Right? That's not balanced. Don't worry about that. We can even break down elements even further if we were to use some really, really intense means. For example, any element can be broken down into its nuclei and electrons, right? You have the central nucleus, and then you have the electron cloud around it. We can then break down the nucleus even further into protons and neutrons. And then we can go even further. We can identify quarks, right? The protons and neutrons are made up of quarks. And we have this flow chart here, matter, right? How can we separate these? We can separate them by physical means, heterogeneous, homogeneous, right? If we separate them all the way down until we run into pure substances, right? Is it a compound? Is it an element? The atom. Then we have the electrons and the neutrons. Then we have protons and neutrons being broken down into quarks. Notice that there are no quarks underneath electrons. All right, guys, that's it for Chapter 1. Check out the next playlist.